Good morning, children. Welcome back to the science class. Before we go into today's learning, let's do a small recap now. In the previous class, we learnt about impulsive force, that is, a large force acting for a very short interval of time. Then we learnt about Newton's third law of motion. According to this law, for every action, there is an equal and opposite reaction. Then we learnt about law of conservation of linear momentum. According to this law, the absence of an external force, the algebraic sum of the momentum after collision is numerically equal to the algebraic sum of the momentum before collision. Today we are going to learn about a new topic, which is nothing but Newton's universal law of gravitation. According to this law, every particle of matter in this universe attracts every other particle with a force, and this force is directly proportional to the product of the masses and inversely proportional to the square of the distance between the center of these masses. Let us consider two bodies of masses m1 and m2, and their forces are F1 and F2, and they are separated by a distance r, where force is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. Where F is directly proportional to m1 m2 by r square, or we can write F is equal to g m1 m2 by r square, and the unit of g is nm square kg minus 1. Now tell me, children, what is acceleration due to gravity? When you throw any object upwards, its velocity decreases and then it falls down due to gravitational force. The velocity of the object keeps changing as it falls down. This change in velocity must be due to the force acting on the body. The acceleration of the body is due to the Earth's gravitational force. So it is called as acceleration due to the gravitational force of the Earth, or acceleration due to gravity of the Earth. Next, let us learn about the relation between g and g. That is, small g is the acceleration due to gravity and capital G is the gravitational constant. Let us consider the Earth of mass m. When a body rests on the surface of the Earth, it is acted upon by the gravitational force of the Earth. Let small m be the mass of the body. According to Newton's law of gravitation, force is equal to gmm by r square, where capital R is the radius of the Earth and small r be the radius of the body. By Newton's second law of motion, force is equal to mass into acceleration. Since we are using acceleration due to gravity, instead of a we can write small g. Now we can equate the two equations, Newton's law of gravitation and Newton's second law of motion. That is, F is equal to gmm by r square and F is equal to m into g. Now m get cancelled, and so g is equal to gm by r square. That is, acceleration due to gravity is equal to gm by r square. Next, let us learn how to calculate the mass of the Earth. We already know the formula for acceleration due to gravity, which is nothing but gm by r square. So the value of m will be nothing but gr square by g. Now by substituting the values of g, r and g in the formula m, where acceleration due to gravity is 9.8 meter per second square and the radius of the Earth will be 6.37 into 10 power 6, and the value of gravitational constant will be 6.674 into 10 power minus 11. So by substituting all these values, finally we will get the mass of the Earth will be 5.972 into 10 power 24 kg. Next, let us learn about the variation of acceleration due to gravity. Since g depends on the geometric radius of the earth, its value changes from one place to another on the surface of the earth. The geometric radius of the earth is maximum in the equator and minimum in the polar region. That is, the value of g is maximum in the polar region and minimum in the equatorial region. When you move to a higher altitude from the surface of the earth, the value of g reduces. When you move deep below the surface of the earth, even then the value of g reduces. And when finally we see that the value of g is 0 at the center of the earth. Since g is inversely proportional to the square of the radius of the earth. From this we know that when r is more, g value will be less. When r is less, g value will be more. Now let us learn about the difference between the mass and the weight. Mass is the quantity of matter in a body. Weight is the force by which the earth attracts towards its center. Mass is a scalar quantity. Weight is a vector quantity. Mass of a body is always constant everywhere in the universe, but the weight of the body varies from place to place and becomes 0 on the center of the earth. Mass of a moving body can be calculated as m is equal to F by A. Weight of the body is weight is equal to m into g. Mass can be determined by ordinary balance. Weight can be measured by spring balance. Unit of mass in SI system will be kilogram. Unit of weight in SI system will be Newton. Now let us learn about apparent weight. When we are in the process of upward and downward motion, the weight we feel is not same as your actual weight. Weight which is different from actual weight, we say it as the apparent weight. Apparent weight is the weight of the body acquired due to action of gravity and other external forces acting on the body. Let us say the mass of a person be m and the weight will be equal to m into g. When a person is inside a lift, the weight of the person acts downwards. The ground gives a reaction force which will be in the opposite direction. So it's a reaction force which will be in the opposite. When lift is at rest, the two forces are same. Now we are going to learn about the apparent weight of a person in a moving lift. Now first let us see the lift moving upward with an acceleration A. When lift is moving upwards, the reaction force will be greater and therefore the net force will be equal to R minus W. So force is nothing but mass into acceleration, which is equal to R minus W, which is actually the weight of the person acting downwards. So we can bring R towards this side. So it will be MA plus MG, and R is equal to M is common, we can take it outside, which is A plus G. In the second case, lift is moving downwards with an acceleration A. Lift is moving downwards, W will be more. So the net force will be equal to W minus R. So where F is equal to MA is equal to mg minus R. So R will be equal to mg minus MA, or R will be equal to M into G minus A. Now when lift is at rest, acceleration will be equal to 0. So W will be equal to R. So that is mg equal to R, or R is equal to weight of the person acting downwards. Finally, when the lift is falling down freely, acceleration will be equal to acceleration due to gravity. We already know that when lift is moving downwards, R is equal to M into G minus A. So we can write that m into g minus, instead of a we can write g, since a is equal to g. So r is equal to m into 0, or r is equal to 0. That is, the apparent weight is equal to 0. Now let us see all the cases. When lift is moving upward, the reaction will be greater than W. That is actual weight of the person. That is, apparent weight will be greater than the actual weight. When lift is moving downwards, R will be less than W. That is, the apparent weight will be lesser than the actual weight. Then in the third case, when lift is at rest, R will be equal to W. That is, apparent weight is equal to actual weight. And finally, when lift is falling downwards freely, R will be equal to 0. That is, apparent weight will be equal to 0. In this picture, you can see when acceleration is 0, the apparent weight is equal to the actual weight. When the acceleration is moving upwards, the apparent weight will be greater than the normal weight. When the acceleration is towards downwards, the apparent weight is less than the normal weight. When acceleration is equal to g, the apparent weight is equal to 0. Children, have you gone to an amusement park and taken a ride in a roller coaster or in a giant wheel? During the fast downward and upward movement, how did you feel? It's amazing. You actually feel as if you're falling freely without having any weight. This is due to the phenomenon of weightlessness. Sometimes you experience the same feeling while traveling in a lift. The same effect takes place while falling freely in a roller coaster or on a swing or in a vertical giant wheel. You feel an apparent weight loss and weight gain when you are moving up and down in such rides. Children, have you seen astronauts floating in the orbiting space station? Some of us believe that they do not experience any gravitational force of the earth, so they float. But this is absolutely wrong. Hi children, this is Kalpana Chawla. Do you think astronauts float in the space station? But they are not floating but falling down freely around the earth due to the huge orbital velocity. Since space station and astronauts have equal acceleration, they are under free fall condition. Hence, both astronauts and the space station, they are in the state of weightlessness. Next, let's learn about the applications of Newton's law of gravitation. The dimensions of the heavenly bodies can be measured using the gravitational law. It helps in discovering new stars and planets. Mass of the star can be calculated using the law of gravitation. It helps to explain the germination of roots. It helps to predict the path of the astronomical bodies. Dear children, with this lesson gets over. Please go through the lesson. Wash your hands regularly. Stay safe. Thank you. Children, don't forget to watch the robotic rover to Mars in enrichment link.